All right, cuckerinos. This is the last ingredient we need to just like put the finishing touches on our polymorphic definitions to make them just like, ideal. Chef's kiss. That's what we're going for. Okay. So what this last ingredient is a way of telling Coq, hey, I want you to always treat this argument as implicit. So the way we can do that is with the arguments directive in vernacular. So the arguments command here names a function or a constructor and says, hey, some of these arguments should always just default to underscore. Don't even make me write the underscore. Just fill it in for me automatically. And you put curly braces around those arguments. Now, you're never going to have to write this yourself. This is not a big deal. We just want you to know how it works so that you're sort of familiar. You will have to write curly braces yourself later on. We'll see. But you won't need to use arguments. You just need to know about it. Okay, so here we're saying, look, for nil, I never want to write the type argument ever. Just figure it out. Figure it out from context. You'll know what's going on. For cons, figure out the type argument. I'll still name the head and tail of the list. Don't worry about that. But figure this one out on your own. For the length function, I don't want to tell you what's in my list when I'm computing its length because it doesn't matter. I just want to tell you the list that I'm going to compute the length of. And lastly, for repeat, I don't want to have to tell you what the type is, just figure out the type of these elements. If you've been following along and you changed the type of x to elem or something, you'll actually get an error message here. The names you're giving here have to be the actual names of the arguments to get it right. Okay, but check out list 1, 2, 3 double prime. Look at this. Cons 1, cons 2, cons 3, cons nil. Beautiful. Right? It just figured it out. We didn't have to write any of the types. It looks nice, I think. Okay, when you're declaring a function, you can mark something as implicit by putting it in curly braces. The general rule is you really want the type arguments to be implicit and kind of nothing else, right? What would it mean for Coq to try to guess the element? It's like, well, I don't know. What do you want a repeated list of? Like, that's weird. It's hard to guess. One thing I want to note is that once you've written this implicit argument here, it applies everywhere immediately, even in your recursive calls. Look at this recursive call to repeat triple prime. We don't have to mention x at all anywhere, not in nil or cons, but that's no surprise, right? Nil and cons have implicit arguments anyway. But even repeat with its implicit type argument, great, we just call the function. So we showed you this notation much, much earlier when we wrote, I think, const fun, just to show you functions that generate others. But now you can see, though, this is what that notation means. It says, I'm taking some type parameter, and I don't even want to talk about it. Like, just figure it out. You work it out. It's not complicated, is what we're saying to Coq. So let's write a couple other list functions. So I'm just going to show them to you. I'm not going to say what they do. Their names are a little bit suggestive, not in that way. And then see if you can sort of guess what they do, and then I'll tell you what they really do. So here's a function app. Takes two arguments, L1, L2, of some list type x, and it returns a list x. Okay, that can let you think a little bit. Okay, it's returning just one list on the other side. Interesting. When L1 is empty, it just returns L2. If L1 is cons ht, right, here's the head of L1, here's the tail, then we'll cons h onto app TL2. Think about this for a moment. What do you think this function does? And then for each of the following computes, try to guess what you think the answer is going to be before we compute it. Pause the video if you need. I'll try to give a couple seconds between each compute. Okay, first off, this is a good definition. The next off, let's look at this first compute. Nil, cons 1, 2, nil. Well, we already saw what happened in the nil case. What do you think it is? Just cons 1, cons 2, nil. The list 1, 2. Okay, if I have cons 2, cons 7, nil, apt onto nil, what do we think that means? Well, it'll be the list, just cons 2, cons 7. Okay, let's look at one more. Cons 2, cons 7, nil, app, cons 3, cons 1, cons 0, nil. What's that going to be? 27310. What do you think app stands for? Did I hear you say append? No, because I'm in my house and it's 8 p.m. on a Wednesday. But maybe you said it at home just now. Great. Okay, rev. This function takes the type parameter, takes a list, returns another. From its name, you might already be guessing that this is a function that revs engines. No. What does it do? If the list is empty, it returns the list. Otherwise, if it's h cons t is the list we're looking at, it appends rev t onto the singleton list, the list with one element in it, of cons h nil. What do we think this does? Well, the name may suggest to you a certain behavior. 1, 2 goes to 2, 1. True goes to just true. This function reverses a list. Oh, there's the quiz. I ruined the quiz. Well, now we know. Okay, so in here you've got some exercises where we'd like you to write some of these functions. Some of them are polymorphic, some aren't. Here's a function allB that should return true when every bool in the list is true. There's a sort of question about what should happen if the list is empty. So think about it. There's a what I think is a right answer, and I think you can argue for it, but it is a convention. What I'd like you to do is to see if you can figure out the convention, what it ought to be. Here's another function for lists. Sum. Given a list of gnats, compute the sum. What should it be? Again, it's kind of a question of convention, but I think there's really a well agreed upon right answer for what happens when the list is empty. Okay, last up. Write a function 0 to n that builds a list from 0 to n inclusive. Cox termination requirements are going to mess with you here. You can't count up. You can only go down. So how do you get something from 0 to n? So there's two approaches. You write a helper function, some other fixed point with a name that you make up, or you post-process the list. So you might find it useful to in the middle of a function definition. So you can define your fixed point if it's a helper separately. You can also define it in line. So you can write let fix foo to define a recursive function inside of another function. And that might be useful to you. One thing to note is that you cannot write the return type in this syntax, right? But this syntax turns into letting foo be some fix. Okay, so we want you to write that function too. Okay, that's it. I'm gonna talk about this in this video too. Sometimes it comes up that you have a function with implicit arguments, and you want to say what its type actually is. So it can present problems. So like if you wanted to say just define something else to be nil, that'll go wrong. Kak will say, I couldn't guess the type. And the reason it can't guess is because there's no context. Nothing forces nil to be any particular thing. So one way to fix that is, well, write a type declaration. And then the context that my nil is supposed to have type list nat is enough for Kak to figure out that like, oh, okay, the implicit type parameter for nil, that implicit type argument is nat. The other option is you can take something that has implicit arguments and you put the @ sign, historically called the griddle, which I kind of love, but the language that does this best is probably Russian, which calls it sabachka, which means little dog. It's a little dog with a long tail. No. So you can write an @ before the name of something that has implicit arguments to turn it back into the explicit version. So for example, if I say check @ nil, it has type for all x type list x. If I say just check nil, it'll say list, and then it has this question mark x, where x is a type. This notation is Kak's way of saying, I haven't figured it out yet. Right? I couldn't tell from here what's going on. And so then if we wanted to, for example, talk about nil nat without having to have a type annotation anywhere, you could just write @ nil nat, and then your definition will work fine. And it'll say, oh, what type is my nil prime? It's a list nat. Okay, that's the last thing. The main takeaway here, other than, okay, you've got some relatively challenging exercises here, is if you want a function that's polymorphic over lists, that's generic, that works on lists of any type, you almost certainly want to take that type in curly braces so that people can call your function without specifying the type. Beyond that, okay, there's some nifty Kak stuff happening in the background to sort of automatically do this sort of inference and synthesis and implicit argument substitution. All that happens in the background. You shouldn't have to think about it too much. We just wanted to explain the mechanisms before we dove in and showed you the technical bits. Okay, the rest of this file will be telling you about a couple of other interesting data structures, but this was sort of been the worst technical content that we'll meet in this file. Okay, great. More videos soon.